In Part 8 of this series, Classical Chemical Assay for Small-Scale Miners, Prospectors, and Hobbyists, I discuss some of the intricacies in regards to dissolving rock, soil, and concentrate samples for qualitative and quantitative analysis. Now, in a few older textbooks from back in the day, qualitative is sometimes used in reference to qualitative. However, qualitative is a more precise term that is used. I use the term qualificative in Part 8 of this series. Now, qualificative was used to qualify the constituency of a sample in regards to what the sample was made of. Qualitative was used to describe the quality of the sample, whereas quantitative is a term used for concentration of elements in a sample. Now, I stated that refractory materials are resistive to dissolution in acids. These materials require a different approach for total dissolution. Therefore, in this presentation, I will be discussing the dry part of wet-dry method of dissolvement. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. Fusion is very similar to fire assay techniques. However, samples are smaller in mass. Crucibles are smaller, and there are many different types of crucibles that can be employed. This method of dissolution is commonly used for those difficult to dissolve materials. It is the simplest method employed. With the right mix of flux and the proper choice of a crucible, it eliminates almost all of the concerns associated with this type of procedure or method. When conducting a fusion process, the sample consistency must be minus 200 mesh for a more fluid melt. Fusion temperatures, depending on sample type, will range anywhere from 500 degrees to 1200 degrees centigrade. If your sample does not contain a chemically bound oxygen atom, such as steinite, it will need to be oxidized prior to fusion. To avoid loss of analyte, samples must be dry, totally void of any moisture which may cause sputtering. Fusions are made in crucibles, of which there are many types. The crucible of choice is determined by the nature of the flux that you will use. Sample sizes are smaller for analytical analysis. Large amounts of crucible material mixed with the sample may contaminate the sample as well as shorten the life and usability of the crucible. Excessive temperature should be avoided. Overheating can damage a crucible. For any fusion method, the chemical reactions must be considered. You could conduct a carbonate potassium nitrate fusion using a platinum crucible. However, using hydrochloric acid to dissolve the melt will damage the crucible. The liberated chlorine will attack the platinum. Iron, tin, lead, and compounds that contain arsenic and antimony will reduce to their metallic states. These metals will alloy with the platinum. Also, melts can be contaminated by a crucible. There are a number of crucibles used in laboratories. However, there are 10 most commonly used crucibles. The first is the alumina type. They come in many sizes and shapes, such as those shown and manufactured by Better Ceramics. These crucibles are resistant to acids and alkali melts. However, they can be rapidly attacked by bisulfate melts. They are also brittle and must be handled with care. These crucibles are ideal for low-temperature fusion of acidic and alkali materials. The maximum working temperature should never exceed 1600 degrees centigrade. These crucibles are commonly used for sintering. Borosilicate glass crucibles come in many sizes and shapes also. Some have glass lids and others are filtering crucibles, as shown in the bottom picture. These crucibles are transparent and fragile. These must be handled with care. They also have good thermal properties. Although they are quite resistant to attack, they are not resistive to hydrofluoric acid, phosphoric acids, and alkaline solutions. They have a working temperature of 525 degrees centigrade. Beyond this point, these crucibles start to lose their mechanical strength. The filter type are borosilicate glass crucibles, commonly referred to as Gooch filters, have a working temperature of 110 degrees centigrade. These are used for drying precipitates, followed with acid digestion of the precipitate. The borosilicate or glass crucibles are considered to be general application type crucibles. These too come in many sizes and shapes. Some have lids and some do not. These crucibles are chemically inert. That is, they are not chemically reactive. However, above 430 degrees centigrade, they will slowly oxidize. This is why these crucibles are not recommended for long fusion time or when samples are reduced. Now, these units are disposable. By disposing after use reduces the possibility of cross-contamination of your samples. However, graphite crucibles are also cost-effective due to their low cost per unit. Now, these crucibles may be cleaned. Just follow the manufacturer's cleaning instructions. As shown in this picture from Thomas Scientifics, these crucibles also come in a variety of styles. They are commonly used for molten metal hydroxide and sodium peroxide fusions. They are also suitable for use with strong alkaline solutions. Compared to the cost of platinum and zirconium crucibles, nickel crucibles can be a cost-effective replacement due to the lower cost per unit. The working temperature is 350 degrees centigrade. As the temperature goes up, the lifespan of these crucibles starts to diminish, somewhere between 350 and 600 degrees centigrade. This is due to oxidation. Between 600 and 800 degrees centigrade, the life of the crucible is dramatically reduced. Now, above 800 degrees centigrade, oxidation will be severe. The oxide file is tightly adhering to the crucible between 400 and 600 degrees centigrade. These crucibles are very expensive. They are said to be virtually resistant to acids, and that includes hydrofluoric acid. However, these crucibles will dissolve in aqua regia, which is 3 parts hydrochloric acid and 1 part nitric acid. Now, they will dissolve in chlorine or bromine water, but they are adequately resistive to orthophosphoric acid and phosphoric acids in general. They will alloy with mercury, tin, lead, gold, copper, silicon, zinc, cadmium, aluminum, bismuth, and iron. They will become permeable to hydrogen gas or red heat, which is a reducing agent. Visually, the red heat range is between 500 and 1000 degrees centigrade. Now, these crucibles will also react with sulfur, selenium, tellurium, phosphorus, arsenic, antimony, boron, and carbon, all of which will damage them. The crucibles are soft and easily deformed and thus be handled with care. They are usually alloyed by the manufacturer with iridium, gold, or ruthenium for strength, never to be used for sodium peroxide fusions. Now, most laboratories use these crucibles for high temperature or corrosive applications. Now, due to the cost, it's best advised to recycle damaged crucibles for precious metal recovery if possible. Porcelain crucibles are one of the most commonly used crucibles in a laboratory. They are used for high temperature applications. The working temperature range limit is 1100 degrees centigrade. Although these crucibles are resistant to most acids and solutions, they are made of porcelain, which is easily attacked by hydrofluoric acid, phosphoric acids, and alkaline solutions. These crucibles are either opaque or transparent. They are fragile and should be handled with care. The cost per unit is more expensive than glass. They have good thermal properties up to 1150 degrees centigrade and can be used for short-timed applications up to 1250 degrees centigrade. Now, quartz crucibles, having similar properties with borosilicate glass, can be easily attacked by hydrofluoric acid, phosphoric acids, and alkaline solutions. The main use of these crucibles is for high temperature applications. In a wet-dry method, fluxes are used to help break down the matrices of resistant samples during fusion. The dry method is also used for making glass discs. For XRF analysis, that's where other non-flux elements are used in addition to the flux. Anyway, fluxes are primarily used to lower the fusion temperature of a sample. At times, they are mixed to promote oxidation of the sample for decomposition. A flux can be either basic, acidic, oxidizing, or reducing. Acidic fluxes are used to decompose basic samples, and basic fluxes are used to decompose those acidic samples. Oxidizing and reducing fluxes will be discussed in the next few slides also. In regards to basic and acidic fluxes, the most common basic fluxes are sodium carbonate, potassium carbonate, sodium hydroxide, sodium peroxide, sodium tetraborate, and lithium metaborate. Sodium tetraborate can be hydrous, meaning that the compound contains water, and anhydrous. The anhydrous version is commonly referred to as borax glass. The other is just a borax powder that can be turned into glass just by fusion, then pulverization to powder. The most common acidic fluxes are potassium bisulfate, potassium pyrosulfate, hydrofluoride such as ammonium hydrogen fluoride, and then there are salts or esters of fluoroboric acid and tetrafluoroboric acid. Then we have boric acid and lithium tetraborate. For example, silica, being quartz, is very difficult to decompose, especially in a lithium tetraborate fusion. Silica is an acidic compound. Lithium tetraborate is an acidic flux. In order to decompose the quartz, a basic flux will need to be used. Lithium metaborate would be the choice. The lithium metaborate, being a basic flux, increases the basicity of the system, at the same time decreases the fusion temperature of the sample. The result is a better homogenized decomposition of the oxides in the melt. In the next few slides, I want to talk about some of these fluxes in a little more detail. It is to give some understanding as to why these fluxes are used. Sodium carbonate is the most commonly used flux during fusion for decomposition. Characteristically, it is basic or it can be alkaline due to its sodium component. Usually, this flux is combined with the sample homogeneously in ratios of 5:1 or 10:1. The fusion temperature ranges between 1000 degrees centigrade to 1200 degrees centigrade. The crucibles that are used are nickel, iron, platinum, or of a platinum alloy. Sodium carbonate is used to decompose silicates, sulfates, oxides, fluorides, phosphates, and more. Mixed with potassium nitrate with a ratio of 1/4 or 1/2 creates a good basic oxidizing mixture for sulfides, arsenides, and other reducing materials. A 1-to-1 mixture with sodium peroxide will decompose ilmenite. By mixing borate with the same sample ratio will decompose considerite, including others. Basic samples will need a higher flux to sample ratio, as noted in the second bullet. This flux is also commonly used, but it requires dehydration prior to use. This can be achieved by placing it into an oven for about an hour at 270 degrees centigrade, then weighing. This step is repeated until the weight of the material does not change. It is then cooled in a desiccator and stored in an airtight container. This reduces sputtering during fusion. The fusion temperature range is the same as sodium carbonate. The result is a more soluble fusion cake. Mixed with sodium carbonate, this will lower the fusion temperature. The result is a good fusion mixture for fluoride determinations. Take note, any excess of potassium salts may contaminate the precipitate more than an excess of sodium salts. Both sodium and potassium hydroxides have melting points of 320 degrees centigrade, approximately. They are very strong basic fluxes that are used to decompose rock samples that contain alkaline earth metals, sulfates, carbonates, silicates, chlorides, and more. Now these two chemicals are very hard to obtain in highly purified form, and because of this fact they are very expensive. Some manufacturers or suppliers will charge up to $250 or more for 500 grams of product. Product that is less than 99% pure may not be suitable for trace element analysis. Now these two chemicals will attack your crucibles. Silver crucibles are the most resistant to attack. Sodium peroxide is an extremely powerful oxidizing compound. It is also very hygroscopic, that is, it likes to absorb moisture. It has a melting point, MP, of 460 degrees centigrade. Mixed with sodium hydroxide, it makes for a more fluid melt. Crucible used are platinum, nickel, and iron. Sodium peroxide is used to decompose rare earth phosphates, tungsten, niobium minerals, or silicates, etc. It is also used to decompose refractory minerals such as cassiterite, corundum, zircon, and ilmenite. Caution must be taken when using this chemical. Due to its highly oxidizing power, it is very reactive. The short segment is a reaction between a mixture of sodium hydroxide, a sulfur compound, and a moistened glass rod. Sodium tetraborate is commonly referred to as borax or borax glass. It comes in two flavors: hydrous, meaning it has or contains water, and anhydrous, means it's perfectly dry. It is easier to purchase the anhydrous type, however. One can simply buy a box of pure borax off your grocery shelf and melt it into a glass, then pulverize into a powder and store it in a sealed container. This flux is commonly used in fire assay, as it has an alkaline or basic characteristics, and it is commonly used as a bead test in qualitative analysis, as described in parts 1 through 4 in this series. This flux is commonly used to attack refractory oxides such as tantalum, titanium, niobium, boron, etc. The resulting fusion cake is then dissolved in hydrofluoric acid, then evaporated with sulfuric acid to remove the boron and fluoride as boron tetrafluoride gas. The downside is that borax adds a large amount of sodium salts to the solution. Now, boric oxide, commonly referred to as boron tetroxide, has a similar use as borax. However, it is a high temperature flux. Lithium tetra and metaborates are commonly used for the analysis of rocks and minerals, that is, ores and concentrates. Now, these reagents are usually used for instrumental analysis, but not always for this purpose. These two reagents will not damage platinum crucibles if they are treated in oxidizing conditions, and they will not stick to or wet these crucibles. The advantage is they will decompose most rock types and minerals. The resulting fusion cakes are easily dissolved in diluted acids. Fusion temperatures range between 850 and 950 degrees centigrade. The flux to sample ratios range from 3 to 1 to 10 to 1, all of which depends on sample type. Tetraborate is more acidic than metaborate, and therefore it is used to decompose ore and concentrates that have basic characteristics, such as dolomite, whereas lithium metaborate is used for those acidic ores, for example, aluminum-bearing quartz samples such as chalcedony. Potassium pyrosulfate is an acidic flux that is used to decompose the ore types in the R2O3 group of compounds, such as hematite, which has the formula Fe2O3. It is very effective on oxide ores and concentrates, but less effective on silicates. Potassium pyrosulfate will not attack porcelain or silica crucibles, and therefore the choice of crucible to use. However, it will attack platinum crucibles at high temperatures. Now, potassium pyrosulfate is also used at times to clean platinum crucibles. Well, this concludes part 9 of this series titled Classical Assay for Small-Scale Miners, Prospectors, and Hobbyists. In this presentation, I discussed fusion in regards to decomposition. I introduced some of the more common fusion fluxes that are used in a way that I hope was understandable to anyone without a chemistry background. In part 10, when published soon, I will be going a little deeper into the realm of fusion by discussing some of the uses of fluxing reagents, the use of bonds, and other methods for decomposition of hard-to-decompose samples. I hope this presentation was informative and of benefit to you. If you know of someone who would or could obtain some benefit from this presentation, please give it a thumbs up and a share, and I hope this will entice you to view part 10 when it is published. This is my only reward. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.